Welcome to the lecture on effect of welding parameters. So, we discussed about the heat flow during the welding. We talked about the different equations which represent the heat flow equations, and also about the temperature distributions in the welding zone, that is where the molten metal is there, and then heat is dissipated from that zone towards the parent metal side. So, then we will talk about the effect of different welding parameters, like you have the pool shape, the velocity of welding and all that. So, in this lecture we are going to have the discussion about those issues. So, coming to the effect of the pool shape. So, as the heat input and welding speed V both increase, the weld pool becomes more elongated, shifting from elliptical to teardrop shaped. So, basically as you increase that heat input and welding speed both, in that case initially when your V is less and heat input is also less, then the pool is basically in the form of elliptical, and then so because you are moving in one direction, so you will have elliptical type of pool. But as you increase, so as the speed is increased, then the length width ratio becomes more and more the geometric center of the pool lags behind the electrode tip. So, we can see that when if there has been work carried on, and as you increase this velocity, suppose the GTAW of stainless steel 304 was carried out, and the velocity was increased, and also other parameters. So, how the pool shape looks like when so you have the 304 stainless steel welding, and this was done using the GTAW. So, what was seen that when when your the parameters are like it is done at 35 ampere current, 7.4 volt is the voltage, and the velocity is taken as 0.42 mm per second. So, at that point of time your weld pool shape was going like this. So, this is the tip of the electrode. So, and if you increase, so as we discussed that here we are increasing the Q also, like the heat input, and that will depend upon the current and the voltage. So, if you increase this to 70 ampere and the voltage is increased to 8.4 volt suppose, and also the velocity is increased to 2.55 mm per second. So, in that case your pool will change, and this pool will be now looking as if it will go like this. So, it will be your pool will be appearing like this. So, in this case, so this is your in this case direction you are doing the welding. So, the pool earlier it was elliptical and now it is elongated, and if you further increase the current to 100 ampere, and if it is the voltage is to 9 volt and the velocity is further increased to 4.2 meter per second. So, it is the work by Smolik that is reported. So, then in that case your pool becomes it goes like this. So, the pool will become in the shape of the teardrop. So, visibly it can be seen that as you increase the heat input, and also if the velocity is increased, in that case your pool shape becomes changed. So, it is changed from the elliptic to the teardrop type of case shape, and that will be normally. So, you are moving you are doing the welding in this direction. Now, if you do for the stainless steel and if you do for the aluminum, then also you can have a visible you can more visibly see in the case of stainless steel, because aluminum is more conductive. So, even for the there has been a certain observation, and it has been seen with a particular heat input, and also the velocity, especially at larger velocity, it was seen that your sharp pull end was seen in the case of stainless steel. So, it is because of the larger velocity which is there in the case of this that basically the larger velocity will give you such kind of the pool shape. Now, if there is another curve which will talk about the variation of the cooling rates, and that can be seen. So, that is another effect which is to be understood by us. So, that is the cooling rate and the temperature gradient. So, this is another parameter which is important one, where we have to understand that the ratio EI upon V, it represents the amount of heat input per unit length of weld. So, and we have, if you increase the EI by V, that will decrease the cooling rate. So, that means the slope basically changes. So, that can be seen by by looking at again the another kind of curve. So, if you go for the effect of cooling rate. So, the cooling rate, as we discussed, that you have the once the liquid metal is is there and it is dissipating the heat towards the all the sides. So, depending upon how it is dissipating the heat, you will have the presence of the cooling rate, you will have the setup of cooling rate depending upon the change in temperature what you observe at different positions from that point. So, if you do the cooling rate for if you are having the different velocity and you have different value of the EI upon V. So, based on that you will have the temperature distribution. So, that can be found out. So, if again we will see that how it varies. So, for the aluminum it was done. So, there is work by Lee. So, that tells that when if you take the temperature in the ordinate axis and on abscissa if you have the time. So, if you plot, so you will have plots coming like this one, you will have one plot this way, you will be another plot. So, this way the plot goes. So, you will have A, B, C and D, like that the plot varies. Here you will have the temperature, so it is somewhere close to 900 degrees centigrade, and this is the time. So, time is in terms of second, and the second is 0.4, 0.8, then 1.2, like that it moves in this fashion. Now, this A was corresponding to the V of 10 centimeter per minute, and EI upon V, this was 15.4 kilojoule per centimeter. So, this is the value of the EI upon V for the A curve, and if you go for B, B is corresponding to V of 15 centimeter per minute, and EI upon V value for that is 9.79 kilojoule per centimeter. Similarly, C has V of 20 centimeter per minute, and the EI upon V is having 7.34 kilojoule per centimeter. So that way, as you see, this value will be changing. Now what we see here, it can be seen, so that is seen that your if you increase the EI upon V, it will be decreasing the cooling rate. So EI upon V value increasing. Now what you see from this curve, the temperature is decreasing with time. But in this case, your temperature time, the difference of temperature with time will be more in case of D as compared to A. It means that if you increase the EI upon V value, that is in this side. So if you are moving, if you are increasing this EI upon V value, so towards A, your temperature difference is less, and once your temperature difference is less, it means your cooling rate will be less. So cooling rate will be more in case of curve A as compared to curve B, and then B is less as compared to to C. So C has more cooling rate, C experiences more cooling rate than B, and B more as compared to A, so like that. So that way it can be seen that as you increase this EI upon V value, so increase so that way your decrease of the cooling rate is observed in such cases. Now this has also been seen for the different welding processes, and for different welding process the curve was drawn again, and if you compare, so you can have the comparison for the different welding process, like you have the arc welding or you have the electroslag welding. Now in the case of arc welding, that EI by value, V value, and the or Q by V value, and in case of the electroslag welding, Q by V value will be different. So what was seen that in the case of the comparative study between the time and temperature and time for the two welding process. So for the arc welding, what was it was seen that it was coming it was coming like this. So this was going like that. So this is for the arc weld, and if you look at the electroslag weld, so for electroslag weld it goes and then it will be moving like this. So this is for the electroslag weld. Now if you see in this arc weld, your temperature will is coming down very quickly, and here the temperature basically is very it goes somewhat higher and then it comes very slowly in this fashion. So the cooling rate in the case of arc weld is quite high, because the slope is quite high in this case of arc weld as compared to electroslag welding. As you also understand that in the case of electroslag welding, the heat input, that is Q upon V, basically Q by V value is very high in this case, and because the Q by V value is very high in this case, so your cooling rate is very small in such cases, in the case of the electroslag welding. So now the thing is that you have the effect of the heat input, then also you can have the variation of the cooling rate by the action of preheat. So, welding speed, preheat, all these have the effect on the cooling rate. So, many a times we do the preheating, and then because once you preheat, the cooling rate will decrease. So, that is another way to have the different kind of structure, because ultimately these these lines, these temperature and time histories, they are basically instrumental in predicting the properties of the material, because we will study about it, that they are useful for knowing that what kind of transformation will be going further, and what type of transformational products will be formed. So, that can be understood by these processes. The next parameter which is important is the power density distribution. So, power density distribution, you have the power density distribution of heat source as an important parameter, and so under the same heat input and welding speed, the weld penetration will decrease with decreasing power density of the heat source. So, you have different type of heat sources, and you have the different power densities. So, that can be understood by the by the figures. So, we will have the the effect of the power density distribution. Now, you can understand that if you have the different power density distribution, you will have the different weld shape. So, if your power density distribution, that can be you have the Gaussian type of we take that Gaussian shape. So, if you take that power density distribution as the Gaussian one, so what we see that if this is like 20, then you have 40 and 60. So, watt per meter square, that is the power density. Now, for such cases, if you take the weld shape, so weld shape will go like this. Now, if you change the power density, so if the power density distribution is changed to this size, suppose it is it goes like this, where this is your 20 and this is 40. So, it is changed now. Now, if the power density distribution is changed, then that will lead to the pool shape, and it will go like from here it will come, and then it is the power density distribution. So, the pool shape will go like this. Now, if there is further the change in the power density distribution, and it comes of say the shape say further less. So, it is coming like this. So, this is 20 watt per meter square. In that case, your weld pool becomes like this. So, what we see that there is a visible change in the case of the weld pool shape, or the penetration in the case of the change in the power density distribution. So, the weld penetration will be decreasing. So, as you are decreasing the power density in this direction, you are decreasing the power density. So, the weld penetration is basically here, the penetration is quite high. So, if the penetration, suppose if you are taking the penetration and the power density very high, say if the power density is going like this, and this is 200 and this is 100. So, that is your watt per meter millimeter square. So, this is your the density of the power power density distribution, that is in terms of watt per mm square. So, in this case what we see that you have, if you this is from here, this is 4 mm. So, your your pull shape goes like this. So, it will be its penetration will be quite high, it will be quite large penetration it will be providing when your power density density distribution is quite high. So, the thing is that it also depends under the same heat input and also the same plate thickness. So, if you have two you have two types of welding, you have the fillet welding, and if you have say the bead on plate welding. So, if you have two types of welding carried on, in that case your the cooling time is shorter for the fillet welding. So, that is for that is the effect of basically the heat sink. So, what we have understood for this case, what we have seen the effect of the power density distribution of the heat source. Now, the next parameter which we are going to discuss will be the heat sink effect of the workpiece, and in that basically the cooling rate will increase. So, cooling rate increases with the thickness of the workpiece, and it is because a thicker workpiece acts as a better heat sink to cool the weld down. So, next parameter which is there is the heat sink effect of the workpiece, and as we see that the workpiece basically works as a heat sink. So, because the heat which is generated that is being taken away by the workpiece itself. So, in this case as you increase the thickness of the workpiece, so it will be acting as a better heat sink to cool the weld down. So, that way so we are having the example of the fillet welding as on, and also the bead on plate welding. So, if you take the two cases, and if you have the same heat input and for the same thickness, so the cooling time will be shorter for the fillet welding so, and as compared to the bead on plate welding, because of the greater heat sink in this case in the fillet welding. So, that is the difference of the the heat sink different type of that heat sink effect of the workpiece. Now, so what we discussed in this case, we discussed about the varying parameters, and in that we talked about the pool shape, we talked about the cooling rate and the temperature gradient. So, again that temperature gradient and cooling rate that can be seen from one curve, and from there as we see so for different EI1V value how the cooling rate can be found and then its effect can further be predicted, that we will see later. Then we talked about the power density distribution. Now, in the case of power density distribution, as we see power density distribution will be governed by certain physical parameters, like if you look at if you see the electrode tip angle. So, basically it has been seen for the gas tungsten arc welding, when it was seen that your tip angle is smaller, and if you make this tip angle blunt, so you may have the tip angle. So, in this case it is blunt, and in this case it is made taper. So, in this case what we see is that your power density distribution. Now, in this case your power density. So, if you look at the power density distribution in this case, so if you draw the power density distribution, you will be following like this in this case, whereas in such case the power density distribution moves like this. So, the power density distribution basically will be depending upon the tool tip size, tool tip shape also, because that will be for the shape your power density distribution will be varying. Similarly, this will be also depending upon the vertex angle of the conical tip of the tungsten electrode. So, if you change the vertex angle also of the conical tip of tungsten electrode, then as per the observation by the key. So, if your vertex angle is say 30 degree in this case. So, in that case the shape of the gas tungsten arc weld will be like this, and if it is 60 degree. So, in that case your shape will be going like this. Then further, if you have 90 degree, then the shape comes like this, and if it is 180 degree, then the shape of the gas tungsten arc weld will be moving like this. So, basically it has also the similar effect in the case of if you look at this will be the effect of the electrode tip geometry, that is on the shape of the gas tungsten arc welds. So, that is how it looks. So, these are this way this power density distribution is a very important parameter also in the case of welding. Now, you have also there are different methods also to measure this power density distribution, and there has been methods like split anode method, which has been said, and for simplicity we take this power density distribution to be of the Gaussian shape in normal circumstances. So, this was basically this observation was made by one of the researchers, that is Savage, and he has found that if you keep the welding current and the speed and arc gap, if you are keeping these parameters as the constant. So, he found that the depth by width ratio. So, this is what we see in this case. This is the depth upon width ratio. So, depth by width ratio he found this is increasing. So, this increases with increasing vertex angle. So that is of the conical tip of the tungsten electrode. So, just to we discussed about this because you should have we should have the idea about how this power distribution varies, and basically how your how your tip geometry basically will be affecting the arc arc welds. So, as we see that if you are increasing the vertex angle, in that case if you increase, then the depth to width ratio that will be increasing. So, in this case the depth is increasing as the vertex angle is increased, and it has also been reported by another researcher, that was Key. So, he has also seen for the with arc shielding, he has observed the similar phenomena. So, so in a nutshell, we talked about today about the different welding parameters and how they affect the the output parameters, like how the there will be change in the cooling rate, or how there will be change in the pool shape, and how that will be affecting ultimately the welding processes. So, that is what ultimately our aim was, and we will more talk about the other aspects of the heat flow and its related consequences in our coming lectures. Thank you very much.